What we're talking about is hardware description languages, or HDLs. And these are a totally new way of programming typically programmable logic boards. This stuff won't be on the exam at all. It's not technically part of anything. It's sort of extra. So it's stuff that in work may be extremely useful, even for your own personal projects. Because this is how we actually program the boards. We don't, for large projects, use schematic entry. It's just too crazy. So with an HDL, or hardware description language, it looks a little like software that you might already be doing. So it looks a bit like, C or something like that. The difference is that with software, say we had these statements, we have a computer and the computer executes stuff. So first it goes A is equal to 5. And then it goes C is equal to A plus 2, so C is equal to 7. And then it goes F is equal to that value of C plus 3. So, F is equal to 10. And that's, just goes through statement by statement, and that's it. The difference with the hardware is you're actually describing hardware. You're not saying do this, do this, do this, do that. So if you write these statements, you're saying assign the value of A to 5. This statement is saying create an adder and add 2 to A and then assign it to C, and that statement saying the same thing, except we add to 3, which seems like the same as software. The difference is all these statements are executed at the exact same time in parallel. So the value of C will initially be something different because that statement will even execute at the same time that A is being assigned to 5. Likewise, F will be executed at the same time that C is being added in this previous statement. So the advantage of hardware is that you can do a lot more. You can do it all in parallel. So you can create, you can do 20 things in parallel. That's not a problem. So you can create multipliers that are running at the same time as other multipliers and adders and all that. Whereas in software, you have to execute this statement, then this statement, then this statement, and this statement. And you can get, you can do stuff like threads where it looks like you're doing stuff in parallel, but you're not really. At the core level of the CPU, it's still executing one statement, then the next, then the next, then the next. With the hardware, you are doing everything at once. And you can use these hardware description languages for really advanced things. This board is a commercial development board. To give you an idea, it's, I think, $90 US. And on this board, you can actually design a microprocessor. So you can design a CPU. You can choose what goes in the CPU in terms of adders and multipliers. And on top of that, you can then run software. But you can also just put hardware straight in this. To give you some ideas, in my research, I'm doing some stuff using actually this board to brute force encryption keys, and it's just running encryption key checks, and it's doing it thousands of times faster than you can on software, because in a few clock cycles, it's able to do a whole bunch at once. Basically, in 1 or 2 clock cycles, you can do everything because it's all in parallel. So that's where these hardware description languages come in. There's a bunch of different ones, and I'll just go over some general aspects of them. This class won't teach you everything you ever needed to know about them. It's just a very brief introduction. They almost always use this idea of modularity and modules. So a module, and there's different names given to it, but it's basically just a block. In that block, we'll have inputs and outputs. So it's very much like the sub-circuits you've been using in the labs for the schematic. You create a sub-circuit that has a specific function, it does that function, and you can connect it up. So when you connect a big design, you might have a whole bunch of these different modules all wired together, and you'll have adder modules, you'll have memory modules, all sorts of stuff. And in that way, you don't have one massive design, but you create a block, you test it, it works, and then you put it into a bigger design. There's almost always this idea of wires and nets. So And by this I mean wires and nets that have names. So when we're doing logic design in class, we'll give them A, B, C, and it's in the same sort of idea. You'll give them meaningful names. So you might call this AB, and you might call this, is equal. And then elsewhere in your code, you have some other block, and you assign is equal to this input. And then there's an output, and it's whatever that is. So they all of them have this idea that you can assign meaningful names to stuff and give values to that. Most of them, or all of them, have continuous assignments. They'll split into two main things. So continuous assignments are where we actually instigate logic. So for example, in one language we say y is equal to a and b. This output here is equal to the anding of those two variables. And this is just done all the time. So if I said z, if I had a second statement, is equal to a and b, and then x is equal to y and z, how you would physically imagine that existing is it's actually creating another AND gate here, connecting them in parallel, and it's going to name this one Z, and then it's ANDing that to create X. So again, these statements are being executed all at the same time. So at the same time that this is happening, you can see the Z is happening. So this AND gate is just being dropped down like that. So that's the idea of continuous assignment. They have an idea of processes. Processes are blocks where we do stuff in sequence. So this gives you a little ability to do statements that are executed one after another. So for example, you may want to do something, where you add 2 to A, and then if A is greater than 3, you do something. And you want that comparison to happen after you've already added 2. So within processes, we have this idea of doing statements sequentially. The main HDL's hardware description languages you'll come across is probably VHDL and Verilog. Which one to use is almost chance for most people. A lot of it's personal preference. Tends to be what you started using, people will stick with. In industry, Verilog might be a little more popular, but it's hard to claim that. I know they use VHDL here at DAL for most of the courses, so that's what I'm going to be sticking with. They're very similar, so if you know one, you can quickly pick up the other. And the examples, not examples the guy's written, they come from this book, Free Range VHDL, which is freely available, Creative Commons licensed. And there's a link there, so these slides will be online if you want to get the book. And it goes through a ton more examples. If you're interested in this, again, this stuff won't be on the exam, just may be generally useful. So some general VHDL stuff, it's not case sensitive. You can use capitals anywhere you want. So you will see things written differently. For example, some people will always put those ands in capitals. Doesn't matter. White space doesn't matter. All the white space dropped out of here. But what this is saying is that if I had a bunch of extra spaces here, so if I had this second statement look like that, it's all the same. It doesn't matter about those extra spaces. We'll tend to use spaces to make stuff line up, maybe to look nice, but in terms of actual programming language, what the compiler sees, what the computer sees, it just doesn't care at all. You can add comments, and you'll notice that with --. The editors you can use, and you can use that same Xilinx software for doing this, will make comments appear in green so that they sort of blend away a bit from it. And we'll go into this a little more detail. You have statements, a lot like in C. There's if statements, there's case statements, if-else statements, and there's even loop statements, which I'll talk about later. So in VHDL, you'll have these entities that everything starts with. I talked about the idea of you have a module. You have a module that does something, you test it, you drop it down. An entity defines what this module is. So in this example, we have an entity here that has some inputs and outputs. So we have a port name, we have an input, we have an output, and we have in-out. In-out is bidirectional, so you can receive data or send data, and you do that by making it high impedance, what we talked about before, where we tri-state it. So to give you an idea, here's another entity. So here, if I've created a mux, and I have these three inputs, A, B, C, D, and I want to choose which one of them is picked. And I choose it based on these two variables, so select 1 and select 0. So this is just like we had before, where we have S1, S0, and then there's different inputs, A, B, C, D. This is also introducing something else, which is they have what they call vectors. This vector is just 7 wires bundled together. So each of these is actually 7 wires, but it doesn't matter. When you pick A, it's just those 7 wires are all going to be directed to the output A. So that's this standard logic vector that you'll see around. So here is a typical-ish VHDL file. So we can see we have 3 input ports, so you could draw it as having A, B, C, and an output port F. When they say it's standard logic, what this means is that it's just a 1 bit. And the standard logic type is either 1 or 0, or it should be 1 or 0, or Z being high impedance. Potentially it can be other values, but we won't worry about those now. And we have that, and then we have this declaration here where we're saying that's the module, and then this is what the module does. So we have this architecture declaration. So the architecture declaration is telling you exactly how everything works. Within that, we have some internal variables, so we can either define a signal. A signal is something that can be used to connect to the output, essentially. So for example, we have this sig1. So we're saying we're generating this extra variable sig1 that is just a single bit. We also have a variable we're going to use. The advantage of variables is you can see they have these nicer types, like we have an integer here. So you can just assign, 34 to it down here in the bottom. And then you can do stuff like add and compare with the integer. And it's all a lot more native, a lot easier to understand. So that's what a typical-ish VHDL file looks like. Again, this class isn't going to teach you everything about it. I'm trying to sort of introduce you a little bit to what it looks like, and maybe if you're interested or you need to in the future, you have some idea of where to start. So when we have those signals, we have a signal declaration here, we can assign a value to it in a bunch of different ways. So for example, a 3-input NAND gate, if we have ABC and output signal F, we assign it with this angle bracket equals line. And so we would have something like this. So we have an entity, again, we're saying A, B, C, F. So 3 inputs, 1 output. And then you have the architecture, so the architecture is equal, F, and you assign it to not, and we use parentheses then to split off not everything inside that, A and B and C. So that's just a 3-input not gate. You can conditionally assign it. So, for example, assign it to something when some condition is true or something else when not. So here we have the example, implement this logic function in VHDL using using the when condition type thing. So what we're doing here is we're actually seeing, okay, well, we have, let's see, LMN, 3 input variables, and we're actually generating a truth table here. And if you generate the truth table, you can see basically that when L is 0, M is 0, and N is 1, the output's 1, so there's only a few cases that it's 1. L is 1, M is 1, so in this first one, L is 0, L is 1, M is 1. It's also 1. In this case, we don't care about N, so in both the 0 and 1 case. And in all other situations, it's 0, L 0. So this sort of assignment is again occurring continually. So as soon as one of these variables changes, instantly the output is updated, that F3 value. We can also use a case statement, which, similar to the last one, we're using it to, based on some inputs, decide what to do. It tends to be a little cleaner. So we're saying if we want to have a mux, a 4-to-1 mux again, and now what we're going to do, these are just single bits. And MX out. And then we have the select line. In this case, the select line is actually, you'll notice what they called it, the standard logic vector, which is again a bus. So it's 2 bits, but the 2 bits are written in a way that you just have to reference it as a single variable. So in this example, it says with SEL select. So when SEL is 1, 1, the output's D3. When it's 1, 0, it's D2. When it's 0, 1, it's D1. When it's 0, 0, it's D0. And in any other case, it's just set to 0. It may seem crazy because there's 2 bits. There is no other cases. But why they put this is just mostly for simulation reasons, because if these were, you know, high impedance state or some invalid state, it's telling the simulator that put it to 0. You don't really need to worry about that right now, though. As I mentioned, we have an idea of processes. Inside a process, everything occurs sequentially. In VHDL, processes look like this. So we have a process. In here, between begin and end process, these are where the statements are executed one after each other. Here, you can define if you want to use variables or signals inside that process. So, you know, maybe you want something like you want, you know, A is equal to some input plus C, and then you'll have an if A is greater than, you know, 3, then you do something. So you might have something that looks like that. And you would declare the variable A here, and then write the statements here. And we also have what's called a sensitivity list. And this list is a list of all, whenever a variable in that list changes, this process is run. So for example, in this case, what was this, input plus C. If you could put input in here, input in C. So whenever the value of input changes, it's going to do this. Whenever the value of C changes, it's going to do this in sequence. So when we use the processes, the most basic example is one where there's just a single line there. So here's an XOR, for example. So I have a process A and B. Whenever A and B changes, so if A was 1 and it becomes 0, run this. Then F is equal to A XOR B. So this is really just what looks like a different way of writing the same stuff we've been using. The difference here is we're using what we call a behavioral design of it. So when we use a process, we can say, I want you to, set A to 34 and then add 3 and then compare it. What you're really describing is how you want the whole unit to behave. You're not necessarily saying, do it in this exact order. It'll look at that. It'll say, okay, the behavior is, he's comparing A to whatever. He's comparing A to whatever, and then acting upon it. So you're telling the system how it should behave, and it'll figure out the logic required to behave that way. So you're working at a higher level than the stuff we're doing. We've designed, we figured out the behavior, then designed gates to implement it. Here, you can describe the behavior, and then you're done. So there's a longer example where we have, again, a variable A and B, which are integers. So we assign A and B some numbers. We assign A1 something, which is a signal defined there, and then we do some comparison, and based on that comparison, define the output. So that's sort of another example of a process. I had used through these if statements. This is the general form of them. If there's some condition, then we do these statements. Else if, do this. Otherwise, do that. As I mentioned, there's a slide before saying basically you always need the end if to define it. So these are just an easy way to act differently depending on the input variable. So you often use those in processes because you'll say if something, do this, then do that, or do that. So to give you an idea, here's a D flip-flop implemented in VHDL. So you can see we have a box, we have a port D, we have a clock port, and we have a Q output. So that's what this first entity is telling us, because those are the ports. Now we have what actually happens in the design. So we have a process, and the process, as you can see, is only dependent on the clock. So whenever the clock changes, it'll run, not whenever the D input changes. So only when the clock input changes. And we use this construct here, this macro that says if rising edge, and this is just used to only work on the rising edge of the clock. So that'll evaluate to true if the clock, it's the rising edge of the clock. You can do the same thing with the falling edge. So if it is the rising edge of the clock, then Q becomes D. So this is sending forward the value of due to Q. If this statement, you'll notice there's just this, if that, do that. Otherwise, it does not update the value of Q. So that's sort of implied by the fact that there's no other option. So, what sort of I wanted to show you is that we can use VHDL to create state machines. Your handout has the copies of what I'm going to show you here, just for reference. So we had a Mealy state machine described. This is that simple on-off switch. And I think, yeah, this is programmed. So we had, if the on-off switch, you see there's the 4 LEDs that are on. And if you go off, they should turn off. And the bottom one will go on to indicate a beep. So it doesn't do anything if it's off. If it's on, it turns on and beeps. Off, beeps, turns off. So with a Mealy state machine, we just had 2 states, and the output depends on the state and inputs. So there's 3 parts to the VHDL code. The first part is where we basically, where's the first part? Yeah. The first part is we're going to define a few intermediate variables. So you notice we have this state variable, which we actually give it some nice symbolic name. So we call it state on or state off. That's it. We're going to define some things like if the switch is off, the push button for the switch off, push button for the switch on, the lamp output and the buzzer output. So what you can see is I've used these switch off and switch on. to be assigned from the actual physical switch name. So now when we're working with the code, we have some nice names, switch on and switch off. And then likewise, I've assigned the lamp, the state of the lamp, to 4 LEDs, and I've assigned the buzzer to a single output LED. So using these signals, you can see that it makes the code a lot easier to read because we just have these nice names that are much easier to understand than remembering, oh, it was switch 4, what was switch 4 again? So the logic to do the state transition, we just add if the clock changes or the reset changes, run this process. So if reset is 1, we go to the off state. Otherwise, every time there's a rising edge of the clock, run the following stuff. So only on the rising edge. On the falling edge, don't do anything. And all it's doing is it's checking, there's a case statement. So what's the current value of state? Is it S off or is it S on? If it's S off, it just checks the value of the on push button. If the on push button is 1, it updates the state to now be on. Otherwise, otherwise it does nothing basically. It stays in the off state. If the off push button's 1, and we're in the on state, then we likewise flip to the other state. So all this is doing basically is this part here. It's just doing the transitions. It's not dealing with the outputs. So those 4 parts of the if-else statement are doing those 4 transitions. This is the Mealy state machine, so the outputs are determined based on the current inputs in addition to the state variable. We do this asynchronously, which means you'll notice there's no clock. So every time any of those changes, so if the state changes, the on push button changes, or the off push button changes, we have to run this group. So for example, if we're in the on state, if we're already in the on state, and just the off push button changes, then we run this. And what we do is we go through, we go, okay, when S on, the lamp output goes to 1, so we're turning the light on because we're in the on state. That part doesn't matter in the inputs. We also sample the input state, and this is where we update the buzzer. So if we're going to be changing state because we're currently in the on state and the off push button comes on, we set the buzzer to 1. Otherwise the buzzer goes to 0. And we do the same thing with the S off. So all this logic here is doing just the output, again for the Mealy state machine. For the Moore state machine, we just have 4 states instead of 2, but the output logic is just slightly simpler. So this part's the same. You notice we have 2 extra states, the beep on and beep off. And now the state machine, you'll notice, there's S off and S on, but there's also this beep on and beep off state. And the beep on and beep off are just intermediate states that always transition to the next state. The output logic, because it's a Moore, is again based solely on the current state alone. So you can see when we're in a certain state, we just use, based on that, assign the output variables. So we assign, in the on state, lamp is 1, we don't buzz. In the beep on, we buzz. And then same with the beep off, we buzz. So that's a super quick introduction to VHDL and how you can use it for state machines. So what it's showing you is that it's way easier because you don't have to go through the whole design process of, create K-maps for every possible variable. It's also very easy because, you don't really care. If there's 16 input variables, that's fine. There's more code to write, but you're not creating these crazy, this crazy amount of logic. If you're interested in learning VHDL, as I said, this isn't something that will be tested, or I don't think we'll have a lab with it. But there's a lot of examples online. There will be a version of the firmware for this board, or a version of that project file that uses VHDL with some examples that I don't think is up yet. There's a bunch of examples. This website, as I said, there's a totally free book that's pretty short, a few hundred pages, so it's just introductory. There's tons of books. There's at least 10 books in the library dealing with VHDL. This book you can get with your DAO login online, and is pretty good. And that's it. So, thanks for coming. That's the quick